Next, we are going to discuss the meaning of optimal values of the dual variables from the economic perspective. And in particular, we'll show that the optimal values of the dual variables provide the marginal utility of the corresponding resources. Remember, our dual variables correspond to the resource constraints, and we'll show that the optimal value of each variable represents the amount we should be willing to pay for an additional unit of the resource that that variable corresponds to. So we are looking at the same winery example as before. So recall that the first constraint corresponded to the availability of Merlot grapes. We had 9,000 pounds available, and assume that we have an opportunity to purchase P1 pounds of additional Merlot grapes. Then the question is, how much is it going to change our profit? And then this will determine how much we should be willing to pay for this resource while still making at least as much in profit. In some cases, you may have this hard upper bound on the constraint, but there may be an opportunity to get some extra resource, but you have to overpay for it. So then the question is, how much should you be willing to overpay in order for this to still make economical sense for you? Alright, so let's look at what we got here. Since we saw that the optimal values for both x1 and x2 were positive in the optimal solution for primal LP, we know that both dual constraints will be binding at the optimum by complementary slackness, right? So because we know that once x1 star is greater than 0, the corresponding excess variable in the optimal solution for the dual must be 0, therefore the dual constraint will be satisfied at equality. So that's why we'll have 250 times y1 star plus 250 times y2 star is equal to 800. And similarly for the second dual constraint, we'll have 450 times y1 star plus 50 times y2 star is equal to 600. So this means that I can replace 800 with this sum right here in the objective, and similarly I can replace 600 with this sum right here. So therefore we will have z, which is equal to 800 x1 plus 600 x2, will be equal to 250 y1 star plus 250 y2 star multiplied by x1 plus 450 y1 star plus 50 y2 star multiplied by x2. So essentially we are doing the same thing as we have done in the derivation of the weak duality, but here we know that because we are taking the optimal value of the dual variable, we actually have the equality instead of just inequality. And then rearranging the terms, just like we did in the derivation of weak duality, we obtain that the coefficient for y1 star is given by 250 x1 plus 450 x2. Right, so this is equal to 250 x1 plus 450 x2 multiplied by y1 star, and then plus the coefficient for y2 star is going to be 250 x1 plus 50 x2. So far all we wrote here holds for every feasible x, okay, and then these constraints also must hold for every feasible x. Therefore we'll have less than or equal to, we replace this with 9,000 plus p1 times y1 star. And then for this coefficient, this is the left hand side of the second constraint, so it's gonna be 5,000 times y2 star. which is equal to the following. So 9,000 times y1 star plus 5,000 times y2 star is going to give us the optimal objective value for the dual, which is the same as the optimal objective value for the primal, so which is z star. And then what remains is going to be plus p1 y1 star. So from here we can tell that the maximum amount by which my objective value can increase for any feasible x for the primal is bounded by the previous optimal objective, which is z star, plus this term here given by p1, which represents the additional amount of the Merlot grape that we can get, multiplied by the optimal value of the dual variable, which is y1 star. So since y1 star is equal to 1.1, we obtain z star plus 1.1 p1. So this means that by increasing the right hand side of this constraint by 1 unit, so let's say if p1 is equal to 1, we are gonna get no more than $1.10 in extra profit. Alright, so essentially the optimal value of the dual variable here gives us an upper bound on how much we will increase our objective if we add an extra unit of the resource. Note that the way we formulated this model here, we don't specify the price of the grapes, right? So we just assume that we had 9,000 pounds of Merlot and 5,000 pounds of Cabernet Sauvignon grapes available. But typically in profit maximization models, the coefficients that you have for your variables already take into account the price of the resource, because we claim that this model maximizes the profit. So this coefficient of 800 for Bordeaux and 600 for Cabernet Sauvignon already implicitly takes into account the cost of the grapes and other things. So if we increase the right hand side of the first constraint by the amount P1 and resolve our model, then it will give us the optimal solution under the assumption that we pay that regular price for the extra resource that we have here. All right. And with that assumption, our profit still can increase by as much as $1.10 per unit of this additional resource. So this means that we may be willing to pay up to this amount on top of the regular price for the unit of this resource and still have at least the same profit as before. Because say if I had the equality here instead of the inequality, and I added an extra pound of the Merlot grape, then my profit would change from Z star to Z star plus $1.10. Meaning that if I paid my regular amount for this additional unit of my resource, then still I made $1.10 extra in profit. But this means that if I overpaid, for example, $1 for this pound of extra resource in addition to what I usually pay, I would still make 10 cents in profit, right? So I can go up to $1.10 in additional payment that I would make for this extra unit of resource and still break even. And in some situation, satisfying the demand may be critical for future business, so you could be willing to pay this much extra and just break even compared to your optimal solution you had before, but make your customer happy, and this could still make sense for you economically. But if you exceed this amount on top of the regular price, then you will be losing money compared to what you had before. So that's why we call this optimal value of the dual variable the shadow price. So it's the shadow price because this is what you could be willing to pay for an additional unit of your resource on top of the regular price. For example, if our model explicitly stated that, let's say, you pay $2 per pound of Merlot grape, and these costs of grapes are already taken into account in this coefficient of 800 for the variable x1 and 600 for the variable x2, then since your regular price for a pound of Merlot grape is $2 and the shadow price is $1.10, you should be willing to pay up to $3.10 for an additional pound of Merlot grape for this to still make economic sense. If you exceed this amount, you will be losing the money compared to your previous optimal solution. So we concluded that the extra profit will never exceed 1.1 times P1, where 1.1 was the optimal value for the dual variable y1. Therefore, $1.10 per pound is the maximum extra amount the winery should be willing to pay for any additional Merlot grapes. Alright, so similarly, we can do the same analysis to see that the same thing is happening with the second dual variable and the second constraint. So if you are trying to increase the amount of Cabernet Sauvignon grapes, then we can see that our objective can never exceed the previous optimal value plus 2.1 times P2, where 2.1 is the optimal value for Y2 and P2 is the amount by which we can increase the right-hand side of the second constraint. Therefore, we shouldn't be willing to pay more than $2.10 per pound of the additional Cabernet grapes. And just like we mentioned, the additional amount by which the optimal objective function value is improved if the right-hand side of the ith constraint is increased by 1 is called the shadow price for the ith resource constraint. Okay, so and we saw that this shadow price is actually given by the optimal value of the corresponding dual variable. An alternative name for the shadow price is the dual price. And this value is usually reported by solvers. In some cases it's called the shadow price, in some cases it's called the dual price, but in both cases it's the optimal value of the corresponding dual variables.